Hello again. In this video, we're going to find the derivative of the natural exponential function. Now, before we actually find the derivative of the natural exponential function, we're first going to talk about the natural exponential function and where it comes from. Okay, and to see where it comes from, we really need to first talk about exponential functions in general. So a general exponential function, you may remember, is a function that looks like this, where you have some base b raised to the x power. Okay, and in order to come up with the natural exponential function, we're going to start with a general exponential function of the form b raised to the x power. And we're going to answer several questions about this function, and that's going to lead us to this idea of a natural exponential function. Okay, so the first question we're going to ask is, if we have a function, a general exponential function with a base b raised to the x power, then what we're going to try to determine is the derivative of this function evaluated at 0. Now what that's going to do for us is it's going to give us the slope of the tangent line to this function right when x is equal to 0. Okay, well, to find the derivative of this function evaluated at 0, we really need to go back to the definition of a derivative, which is this limit. Okay, so using the limit definition of the derivative, let's find f prime evaluated at 0. Well, it's going to be this limit as h goes to 0 of f evaluated at x plus h, but x is equal to 0 here, right? Because we're evaluating the derivative at 0. So it's really f evaluated at 0 plus h. Okay, minus f evaluated at 0. Again, because x is 0 in this case. All divided by h, right? And then we have to find that limit as h goes to 0. Okay, well, what's f evaluated at h? Well, isn't that just b raised to the h power? And then f evaluated at 0 would just be b raised to the 0 power, which of course is equal to 1. Any base raised to the 0 power would equal 1. And then this is all divided by h, and then we're going to find the limit of it as h goes to 0. Okay, and just to simplify this again, b to the 0 power is 1, so let's write that as 1. Okay, and so whatever this limit is, right, the limit is h goes to 0 of b to the h minus 1 over h, whatever this limit is, that's the derivative of this function evaluated at 0, which is the slope of the tangent line to this function right at x equals 0. So keep that in mind, because the next question we're going to ask is, what's f prime of 0, f prime, the derivative evaluated at 0 for this function, which is really just this exponential function when the base happens to be 2. Okay, well, f prime at 0 should be this limit, except the base is now 2, right? So it's the limit as h goes to 0 of 2 raised to the h power minus 1 over h. And whatever that limit is, will be the derivative of this function evaluated at 0, which, by the way, is the slope of the tangent line to this function at x equals 0. Okay? And of course, if we do this for the function 3 to the x power, right, when the base is equal to 3, then the derivative of this function evaluated at 0 would again be this limit, except the base would be 3. So it would be 3 to the h minus 1 over h. Okay? And again, this would be the slope of the tangent line to this function right when x is equal to 0. Okay, so having said this, what we're going to attempt to do is we're going to find both of these limits, these particular limits, using a table. Now, we can find limits in various ways, but we're going to find the limit of both of these by creating a table. So what we're going to do is we're going to create a table of values where h is heading towards 0, and we're going to try to determine what this gets closer to and what this gets closer to as h heads towards 0. Okay, so if you look at table 3.1, that's exactly what we're doing here. We're letting h go to 0, and we're plugging h into this to see what it gets closer to. And you can see that it's getting closer to this number here, 0.693. Whereas for this one, 3 to the h minus 1 over h, as h goes to 0, it's approaching this number, about 1.099. Now, graphically, what's going on here is if you graph the exponential function 2 to the x power, the graph of that function looks like this. And the slope of the tangent line right at 0 is about 0.693. And if you graph the function 3 to the x power, it looks like this. And the slope of the tangent line right at 0 is about 1.099. Okay, and so here's what we're going to do. We're going to try to find the base right? We're going to try to find some base where this limit, as h goes to 0, of b to the h minus 1 over h, we're going to try to find out for what base is this limit equal to 1. Okay, so we're trying to figure out what base b would we need in order for this particular limit to actually equal 1. Now, going back to this table here, I think you can see that if you want this limit to be 1 as h goes to 0, then the base is going to have to be somewhere between 2 and 3. Because if it's 2, if the base is 2, then this limit is 0.693, and if the base is 3, then this limit is 1.099, roughly. So it stands to reason that you would need a base somewhere between 2 and 3 if you want this limit to equal 1. And I think it's going to be closer to 3 than it is to 2, just looking at this table. Okay? Well, there is such a number. Unfortunately, the number is irrational. It's actually this number here, 2.7182818284859. This continues on forever. There's no pattern to the decimals. It's an irrational number, just like pi is. And so we really can't write down this number exactly, so we use a symbol for it, and we call it e. But notice e is a number between 2 and 3, and it is a little closer to 3 than it is to 2. And it happens to be the number where this limit right here, as h goes to 0, right, b to the h minus 1 over h, the limit of that as h goes to 0 equals 1 when this base here happens to be e, this number right here. Okay, and that's called the natural base. Okay, this is called the natural base. And the natural exponential function would be the function with that particular base, right? E to the x power. That's called the natural exponential function. Okay, so that is where e comes from. E is the number, is the base that would make this limit right here equal 1. We need b to equal that number e that we can't write down exactly because it's irrational. So we call it e. But it's somewhere between 2 and 3, right? It's 2.71 something. Okay, so that's where e comes from. Now, having said that, what we're going to do is we're going to take the natural exponential function, which is e to the x power, right, this, and we're going to try to find the derivative of that function. Okay, so let's do that next, because that's really the big goal in this video, is to find the derivative of the natural exponential function. Okay, so let's find the derivative of e to the x. Well, to find this derivative, we're going to use the limit definition of the derivative again, right, which is this. Okay, so it's the derivative of e to the x is the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, well, what's f evaluated at x plus h? Okay, well, what happens when you plug a number in to this function, like 3? Don't you get e raised to the third power? So if you plug x plus h in, aren't you going to get e raised to the x plus h power? So that's f evaluated at x plus h. Okay, minus f of x, which of course is just e to the x, all over h, and then we find the limit as h goes to 0. Okay, so now what we're going to do is we're going to break this apart. Now you may remember one of the properties of exponents is if you have the same base here, you would add exponents. So e to the x plus h is the same as e to the x times e to the h. Because if the bases are the same, you would add exponents. So these are equal. Now the reason I'm writing it like that is because then you can factor the e to the x out on top. Okay, and you're left with e to the h minus 1 after you factor out e to the x, and then that's divided by h, and then we're going to find the limit as h goes to 0 of that. Now it turns out one of the properties of limits says that we can find this limit by finding the limit of e to the x first, and then multiplying it by the limit of e to the h minus 1 over h. Since this is multiplication, there's a property of limits that say the limit of f of x times g of x is the same as the limit of f of x times the limit of g of x. So we're just using that property here. We can break up the limit across multiplication. Okay, but what's this limit equal to? Well, this limit's equal to 1, right? That's what we just found earlier. We asked this question, right? We posed this question, for what base does this limit equal 1? And the answer we found was this irrational number that we're going to call e. That's when this limit is equal to 1, right? When b is equal to this natural base, e. Okay, so going back to this limit, we know this limit is equal to 1. Okay, and so you end up with the limit as h goes to 0 of e to the x times 1. Right, this whole thing is 1. And let me write it like this just to make it clear. This piece here is equal to 1. Okay, so then we're just left with this limit, the limit of e to the x as h goes to 0. Now be careful here. H is heading towards 0, not x. So relative to h, right? H is changing here, x is not. So as h heads towards 0, you're always getting e to the x back. Think of x as a fixed value. As h goes to 0, this will always be e to the x power. Now, if this was e to the h power, then these values would change, right? Because h is getting closer to 0. But that's not what's happening here. H is getting closer to 0, and then this is just always going to be e to the x. X is not changing, only h is. So this limit is actually equal to e to the x power. And something really strange happens. The derivative of e to the x happens to be e to the x. And we know that because by the very definition of a derivative, which is this limit, that's what happens. That's what we got. Okay, so add this to your rules for derivatives. Okay, this is theorem 3.6 in the book. The derivative of e to the x is simply e to the x. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.